Hello everyone and welcome to my channel. Today we are going to look at the paper by Jean-Charles Rochet, a necessary and sufficient condition for rationalizability in a quasi-linear context. So this is a very famous and very foundational paper in auction theory. And my goal with this video is to do the deep dive on this paper and to try to leave no stones unturned and understand and explain all the proofs and details and connections for that are found in this paper. So this is a screenshot of the first page of this paper. So we can see that this paper was published in 1987. And what I find very interesting here is this remark at the bottom of this first page, where the author expresses gratitude to Rockefeller for suggesting this theory. And hopefully the viewers of my channel know who Tyrell Rockefeller is, and he's a super famous expert and in convex optimization. So many contributions of him. He's in his late 80s and he's very active still. And I've recently watched some of his very recent presentations. So I find it very, very interesting that this basically an economics thing. It's connected to the more general results in the convex optimization theory. And in fact, this the main theorem in this paper appears as a generalization of the result by Rockefeller about the characterization of the subgradients of convex functions. So it has some logistics. So please like and subscribe to the channel if you find this content useful, and maybe post a comment, and also check the description for useful links. I will put the links to the paper and to some other materials, and maybe even including these notes in the description of the video. I would like to thank Felipe Perez and Alexei Ulyanov, my colleagues who helped me a little bit with understanding some nuances of the proofs in this paper. And there is also a very helpful reference that I want to mention: 60 years of cyclic monotonicity, a survey by L. D. Pascal and some other authors, which is available on the archive. And that's a huge review, but a couple of paragraphs there helped me a lot to understand the context and understand better this whole concept of cyclic monotonicity and the role of this paper by Rochet in the whole picture. So I'm going to break this video into 3 parts, close to how it's written in the paper. So the first part, this video, is going to be about the main theorem. We're going to first of all understand the settings, and then we are going to prove the main theorem, which is not a very hard proof. Then we are going to, in the part 2, we are going to look into very important and very well-developed one-dimensional special case where the value function could be general form or almost general form with some restrictions, some conditions on it. And then in part 3, we are going to look into the multidimensional special case. So it's a general multidimensional case, but a special case with a linear value function. And this one where this cyclic monotonicity actually comes up. And this one is probably why this paper is quite famous. So for example, recently there were some advances in optimal mechanisms for multidimensional auctions and using neural networks, deep learning, and those papers are relying on the characterization given in this paper. So this is why this paper is kind of important. So first thing we are going to look into is the definition of this quasi-linear context and the quasi-linear utility function. So the setting of this paper is about the agent who has a private information, which in auction theory is usually called type. It's a vector that belongs to the space of reals of, let's say, dimension m. And the agent submits its information, not necessarily exactly the private information, but a vector of the similar, like of the same dimension called b or bid, into this mechanism, and the mechanism returns back the allocation t, which is also could be multidimensional. And this one belongs to R of maybe a different dimension d. And also the mechanism returns some payment that the agent needs to pay to this mechanism. So it's a p of t, which is just a real number. And the agent then has this function that is called a value function. And this value function says the following: given that the private information of the agent is t, and given the allocation that was given back to by the mechanism when the agent submitted some b to it, what is the value, the monetary value that that the agent gets out of this result? Well, in the simplest case, this, like, the good example here is a linear example. In the linear case, the d and m dimensions would be the same, and in the linear case, this v of t, and I will drop the vector, so it would be more or less clear from the context if I'm talking about one-dimensional or multidimensional case. So here I'm talking about the multidimensional case, but here is the linear case, and in the linear case, this is just a scalar product of t and x. So this is written as x as a sum of each component times of the private value times each component of and this goes each component of x, and this goes from 1 to dimension m. So but it's not necessarily linear. It could be more general than linear. So, well, then this is the value that the agent gets, and this is the payment that the agent pays back. So the utility of the agent with the type t submitting bid b is going to be equal this value function of t, and the outcome of the mechanism b, I'm sorry, the outcome of the mechanism x, given that the agent submitted b, and also the payment according to this mechanism. So this particular form is a quasi-linear utility. And typically this is how we perceive the agents that are profit maximizers. So in my previous videos, I touched on the modern auto bidding theory, where the sellers are value maximizers. So they are concerned about maximizing only this thing, and then the payments only enters into the constraints of their optimization problem. And those would be not an example of not a quasi-linear utility. Well, the next thing that we want to look into is this rationalizability. it's always hard to pronounce and spell it out, so I will explain it and then I will use a different word for this. So this rationalizability thing is saying that there exists. So we're given this mechanism X of B. And this mechanism X of B is rationalizable if is okay, let me spell it like this, is rationalizable if there exists a function, a payment function P of B such that for any value of the agent's type of this agent's private information, it is advantageous for the agent to submit its true value as the bid. So in math, this is going to look like the utility of sending T as the bid is always equals or better than any other strategy, any other bid. So this is a general thing, but in the quasi-linear setting, this would look something like this. So x v of t and x of t minus p of t should always be greater than v of t. So the agent still has its private information the same, but submitting a different bid and potentially getting a different allocation and a different bid. So this is the rationalizability, and the mechanism that is rationalized in this way and equipped with this payment and satisfies this inequality is called truthful, and it's just a much easier word to use. So generally, I will be using this word, and it's a slightly different meaning, but very, very close. So one important thing that Rochet mentions in the introduction to this paper, and there is another paper of him from a couple years before, is that the truthful mechanism could be understood in terms of a taxation principle. So I will now explain what is this taxation principle is. So the taxation principle says that the truthful mechanism can only be presented to the agent as a menu of choices. Basically, the menu where the agent can choose what allocation is optimal given the fixed prices on those allocations. Basically, it's saying that this kind of mechanism, the truthful mechanism, cannot charge different prices on like on the same allocation to the same agent. There is no discrimination of the agent that could be happening there. So let's see how we can see it. So well, first of all, we need to give a mathematical definition of this taxation principle. So the definition here is that there is a menu of possible outcomes, possible allocations. Let's use k, the index k, xk's, and pk's. So there's a menu of these things. And well, the agent chooses the optimal. According to their utility function. So this could be written as the utility of T, just T. So now the agent optimizes over their choices of what bits to submit. This would look like taking the maximum of some value K star from the menu. Of these things, of the utilities of individual menu options. So it's going to be T of X K minus PK. So let's try to prove that, in fact, this is a correct principle, that the mechanism is truthful if and only if it's representable in this menu form. So it's not hard to see. So we need to write out to consider two agents with different private values, private information T1 and T2. They consider like all of them for any T1 and T2. When we have this condition of the mechanism being truthful. So for the agent of type T1, its utility of submitting T1 should be larger or equals to the utility of this agent submitting something else, maybe a T2. And on the other hand, for the agent with the private value T2, it should be the opposite. So submitting T2 should be greater or equals than submitting T1. So let's write it out in for this quasi-linear case. So it's going to be T1 and X of T1 minus P1 greater equals to V of T1, but X of T2 minus wait a second. Here we need to put T1 P of T2. And then for the second guy, we need to write the opposite things. So X of T2 minus P of T2 is greater or equals any other options, I mean any other bin, including T1. P of T. Right, so now we can consider a special case. Case where mechanism X returns the same value for T1 and T2. Let's consider this case, this special case. And let's just call this value X. Well, in that case, we can replace this with V of T1 and X minus P of T1 greater equals V of T1 and X minus P of T2, right? And the second equation is going to say basically the same thing. V of T2 and X minus P of T1. Well, those values, they cancel. And we end up with opposite inequalities. So this inequality is saying that P2 is larger than P1, P of T1, and the other inequality is saying larger or equals, and the other inequality is saying that actually the P of T1 is larger or equals than P2. So from these two inequalities, the only conclusion that could be made is that P of T1 is actually equals to P of T2. Well, and this is the essence of the taxation principle. It's saying that whenever the charge for the same allocation should be the same, regardless of what exactly was the bid submitted. If the mechanism returned the same result, the payment should be the same. Okay, so this is going to be pretty useful to derive this this characterization that we are going to derive and considering the main result of the paper. So I think now we are ready to state the main theorem of the paper. It's the theorem 1 of the paper. And this theorem says the following, that that the allocation rule or mechanism x of t is rationalizable if and only if the following condition holds. And this condition is this more general statement of a cyclic monotonicity base. So this is the first time we are seeing it. So I will try to go a little bit slower and explain this cyclic monotonicity condition, which is actually a slightly more general than the basic cyclic monotonicity condition. So at least according to that review on cyclic monotonicity, this thing is going to be called probably V cyclic monotonicity. And the statement is the following, that consider any sequence of those t's going from T1 to Tn. Consider all those sequences. This mechanism is called cyclic monotone if the following holds with respect to this function v. With respect to this function v, if the following holds, that the sum of v of t k plus 1, so the sum goes from k equals 1 to n, and x of tk minus v of tk and x of tk is less or equals to 0. And to make this statement like make sense, we need to understand what is a Tn plus 1, and we are going to define that Tn plus 1 is going to be equal to T1. So this is actually a cycle. Well, let's first take a look at some examples. especially the linear case and the even more easier one-dimensional linear case as an example. And from that example, we are going to reveal the basic one-dimensional monotonicity. And then we will work on the proof that in both directions. So this is if and only if this mechanism is rationalizable, there exists this function of payments. So if that is actually true, then we can derive that this cyclic monotonicity condition holds, and the other way around. Given that the cyclic monotonicity condition holds, we will find the payment function that is going to make this this mechanism truthful. Okay, so first let's look at an example. So simple example is one-dimensional linear case. So in one-dimensional linear case, we have v of t and x just equals t times x. And let's consider a cycle of just two. So the cycle of t1 and t2. So this is going to be t2 times x t1. So considering k equals 1, we are going to have this minus t1 times x of t1 and plus the second term. The second term is now the k is equals to 2. So we need to take a look at t3, but t3, we have only a cycle of 2. So the t3 is going to be equals to t1. So this is going to be t1 x t2 minus t2 times x of t2. And this should be less or equals than 0. So now let's rearrange the terms a little bit. Let's get this x of t1 out. So we have t2 minus t1 plus x of t2 of actually I'm going to change the sign here, minus, and this is going also to be t2 minus t1. This should be less or equals 0. So again, it's just a little bit more convenient to change the signs here, and it's going to be x of t2 minus t1 minus x of t1 times t2 minus t1. Now it's greater than or equals to 0, so I just change the signs of this inequality, and then I'm going to take this t2 minus t1, this common multiplier out. So it's going to be t2 minus t1 times x of t2 minus x of t1 should be greater or equal 0. And this is a basic one-dimensional monotonistic condition for x. So going back here and understanding what this monotonistic condition is saying, like what monotonicity of what exactly is being asserted here. I think it's rather safe to say that the assertion is about the relationship between this t and x and the v, the value here is this type of monotonicity that we are looking into. So this is actually a generalization of monotonicity and actually a generalization of the cyclic monotonicity. But the regular monotonicity and the regular cyclic monotonicity is retrieved when we are considering this linear case where this one is just a basic scalar product. Okay, so I hope this statement of this theorem is clear. So now we just need to prove it. So let's start by proving that it's this is a necessary condition. Necessary condition. So the necessary condition means that given x of t truthful, prove that it is the cyclic monotone. Okay, so we know what truthful means. So let's consider some arbitrary sequence t1 from t1 to some tn, and let's also remember that tn plus 1 is going to be equal to t1, and then we have this condition that v of t and x of t minus p of t. So in the necessary condition, we know that this function p of t exists because this mechanism is already truthful. So this is always equals or greater or equals than submitting any other t, p of t prime. And in particular, we can go about this this cycle, and it's pretty convenient to do it in the following way. Let's consider like a little bit backwards. Let's consider t1 connecting it to like going like on the cycle backwards. So let's consider the case of t1 being the next one, and the previous one is going to be tn. So in this case, we will start with tn. No, I'm sorry. So yeah, we are going to start with t1. And well, we know that this should be better than any other t, including the tn. So this is going to be better than submitting tn and getting the payment for tn. All right. So let's keep going. Let's now write the same thing for t2. So for t2, it's better or equals to do this over submitting t1. And we can continue this all the way to the last one. So the last one is going to be tn and x of tn minus p of tn is going to be better than doing this tn and x of tn minus 1 minus p of tn minus 1. Well, now consider that we are going to take the sum of all those inequalities all the way to the end. So what are we going to get? Well, it's easy to see that all those payments, they are going to cancel. So for example, this p of t1 is canceling with this p of t1. And this p of tn cancels the previous one, which happens to be on the other side of the cycle. So this P2 is going to cancel with this next one, which is going to appear here. And then this P of Tn minus 1 is going to cancel with the one that is going to appear in this previous line. So all these P cancel each other. Great. So can we now write this? So can we get this cyclic monotonicity out of here? Well, let's see. Let's see. So well, yes, we want to collect on this side. So we are going to get the inequality less than 0. And I'm going to move all the terms to the right-hand side and try to collect the terms. So this is going to be V of okay, let's do T1 and okay, well, so let's start with the easier one. So this is going to be V of T2 and X of T1 minus, so I'm collecting this one and this one minus V of T1 and X of T1. So this is collecting the first term from here and the term from here. So in this way, we are going to collect this cross terms here. So this V of so in this next line, we are going to collect V of T3 and X of T2 minus V of T2 and X of T2. So this is collecting this one and the one from the next line. So this one is going to be together with this one. And now right, and now what we want to finally do is to collect this one. Let me use a different color. This one with the one on the right hand side here. Okay, so those two. Okay. So many more are the terms. And finally, we get this V of T1 and X of Tn. Well, minus V of Tn and X of Tn. Well, and this looks exactly as what we wanted to prove, right? So this is a starting with 1, and this is a k plus 1, and this is a k. So yes, so this looks like we got the proof that from the assumption that this mechanism is truthful, that is, the x of t is equipped with the function p of t in such a way that this condition is true for any t and t prime, and taking an arbitrary cycle, we write those conditions for every pair in the cycle, and then all those p's are canceling, and we end up with the condition which is exactly the statement of this cyclic monotonicity with respect to V. Okay, so now we need to go the other way around. So sufficient. Sufficient condition. So for sufficient condition, we need to assume. So we are going to assume the cyclic monotonicity, the V cyclic monotonicity of x of t, and prove that there exists a function p of t that is going to make it is going to make it truthful. Okay, so let's spend 1 minute writing it all out again. So assume assume for any arbitrary cycle, T1 goes to Tn, and assuming that Tn plus 1 equals to T1, the sum goes from k equals 1 to n, v of tk plus 1, and x of tk minus v of tk and x of tk. So assuming this is equals less or equals 0 for any cycle of t, we need to find a function p of t that for any t1 and t2, we would get v of t1 and x of t1 minus p of t1 is going to be greater or equals v of t1, but submitting a t2 as the bit minus p of t2. Okay, so how we can go about it? We need to introduce a new function, which we're going to call the capital V of t. And this function is introduced in the following way. Let's consider some arbitrary starting point t0. And let's consider all possible sequences of t of those points to reach the value t. Well, among those sequences, we will consider the value of that sequence as this sum. So this is going to be the sum from k equals 1 to yeah, let's be a little bit careful here. I guess to n, and we are going to use t k equals 1 as t0, and well, I guess this needs to go from k equals 1 to n minus 1. So the t of n is going to be equals to t. And this is going to be the value of this sequence. Okay? So this is going to be some v of t and this specific sequence of going there. Well, of the same things, t k plus 1, x of tk minus v of tk and x of t. Well, to define this v of t, we are going to choose the sequence that would make this like the maximum value of all of those. So what we want to do is we want to just slightly rewrite this without this reference to the sequence. So we are going to write it as a v of t. And this is going to be, well, a supremum over all sequences t k from going from 1 to n, where t1 is t0 and tn is t. So let's consider all possible sequences going from t0 to t, and let's find the sequence that has the maximal value according to this definition of the value. So this maximal of those, pairwise differences. Okay. So now consider the following situation. We are given this t0. This is our starting point, and this is a t1, and this is a t2, and those are arbitrary t1 and t2. So, well, let's consider the shortest, or actually this one is like the highest cost sequence to go from t0 to t1. Okay. And let's consider, so this one is the shortest, or I'm sorry, the opposite of the highest value sequence. And let's consider an alternative of first going all the way to t2, and then from t2 going straight to t1. So, well, by definition of v, of this capital V, this is the largest value. So the value of going directly like most optimal way to v of t1, this is by construction is greater equals than first going to t2, and on top of that adding just one more step, and that one more step would be going from t2 to t1. So we put t1 here, and x of t2 minus v of t2 and x of t2. And this is this condition is for any t1 and t2. Okay. Well, now with this we can actually construct the payment function. So we will construct the payment function p of t in the following way. We are going to construct it as a v of t and x of t minus capital V of t. And, well, let's substitute for this into that. So let's do the substitution here, and let's see what we get. So we are going to get on the left hand side, we are going to get v of t1 and x of t1 minus p of t1. This is greater than equals of v of t2. Now I'm substituting the capital V of t2 and x of t2 minus p of t2 plus v of t1 and x of t2 and minus v of t2 and x of t2. Okay, so this one cancels, and we end up with exactly what we wanted to prove. So v of t1 and x of t1 minus P of T1 is always greater than or equals to V of T, yeah, T1 and X of T2 minus P of T2. Well, there is just one problem with the argument. Yes, we got what we wanted. We got that from that we can define this P of T and get this condition, but we've never actually used the cyclic monotonicity condition. So something something is missing. And well, we just need to use it to make sure that those capital V of T are actually well defined, that they are not infinite. And to understand this, we need to consider the V capital of T0. So this is the cycle that starts at T0 and ends at T0. Right, and so this is the case where we know that this cycle is by cyclic monotonicity condition is less or equals than 0. Well, on the other hand, we can just directly take a look at the definitions of V of T and plug in just the most trivial cycle, the cycle that goes just with just contains one point, and it goes from T0 directly back to T0. So in this case, we will plug T0 here and here and here and here in all four cases. There's going to be just only one term in the sum, and this is obviously going to collapse to 0. So here we know that V of T0 is less or equals than 0. And on the other hand, we got that, well, at least one candidate for this V of T0 is actually 0. This is the candidate which is the most simple cycle, just going from T0 back to T0. And yeah, well, given this, we can conclude that this is actually the optimal value, 0, and this is why capital V of T0 actually equals to 0, right? So how can we use it now? Well, we can now consider in this starting point T0 and any arbitrary point T, and we can consider any sequence that goes from T0 to all the way to T, and then one step back. So we know now that this full cycle is going to be V of T0 is going to be less than that. No, I'm sorry. The V of T0 is going to be larger than this by definition, because V capital of T0 is the largest value we can get on any cycle. So, well, this is larger than going to V of T. So going from T0 to T through any possible chain or sequence of T's, and then going straight back. So for going straight back, we have what? We have, need brackets here. For going back, we need to take the end, the next point and then the previous point. So this is going to be T0 X of T minus V of T X of T. Well, on the other hand, we know that V of T0 is actually equals to 0. So this is saying that 0 is V of T plus V of T0 X of T minus V of T X of T. And this just says that there are no cycles here. There's no possible to find any sequence, any cycle of those T's that would, give us more and more value just by cycling over there. And well, this implies that the V of T is finite, because otherwise we would be able to cycle around. So this cycle monotonistic condition just guarantees that there are no cycles in which we could be, cycling forever and getting more and more value and going to infinity. And well, this seems to be surprisingly related to problems in the combinatorial optimization. Like, for example, in the max matching problem, there is also a condition for optimality that that says that a certain graph, a residual graph, would not have cycles with negative costs, because those cycles would be used to get to like kind of like arbitrary better better value function or something like this. So yeah, well, I think this is it. This completes the proof. So we use this cyclic monotonistic condition to actually prove that there are no infinite cycles around here, and from this we get a good definition of this capital V of t, and then we plug it into P, and we get what we wanted. I just wanted to mention that this capital V of t, it's kind of it's the V of t and x of t minus P of t, the way we defined it. But, well, on the other hand, this is the U of t and t. So remember, the U is the utility function. So it turns out that this is the same thing, x of t minus P of t. So, well, this V of t has this meaning of this indirect utility. So this is the utility where we already know that it's the best for the agent to plug his private value as the bit, and this is actually just a function of a single t. So this is just a function of t, and well, this V of t is actually equal to this U of t. So this is it for part 1, and see you in the next one.